To verify trig identities, take a look at this one right here. Maybe at first look, it's hard to tell which side looks more complicated, but usually if it has a fraction, it's more complicated. All right, so that's the one I'm going to deal with. I'm going to try to make this side look like cosecant plus cotangent. All right, that's what we're going for. Now, whenever we see something like 1 minus cosine of alpha like that, you might be thinking to yourself, that looks kind of like a Pythagorean identity, right? So we're going to try to make it look more like a Pythagorean identity. We need something squared, so I'm going to multiply both top and the bottom by the conjugate, which would be 1 plus cosine on the top and the bottom. And so when I multiply the bottom by that, I get 1 minus cosine squared. Okay? Now I'm going to leave the other side alone still. Now this I know. I know 1 minus cosine squared of A. Think back to your Pythagorean identities. That's sine squared. So we have sine of A times 1 plus cosine over sine squared. Yes, one of the signs on the top cancels out with one on the bottom, and so now we have sine of A on the bottom, and so I'm going to split that up. That is 1 over sine of A plus cosine over sine. And I think we know 1 over sine, the reciprocal of sine is cosecant. Not reciprocal, but cosine over sine is cotangent. We look over there, oh my goodness, that's what we were looking for. We've shown that identity right there. We've shown that is true. We've verified it. Let's take a look at this one. Wow, that looks like a lot's going on. All right, it's clear that the left side is more complicated than the right side. Look at the left side here. So much to deal with. So I have this binomial over here on the left, and it just looks like a bunch of craziness. I could change it, bring it down into sines and cosines, probably simplify it down pretty nice, but I notice there is cotangents in both. There's also secants in both. I'm going to factor out what's in common. Cotangent of theta, secant of theta. I'll be left with cosecant squared theta minus cotangent squared theta. So I brought the cotangent out, one of the cotangents out from over there, the secant out, I brought the secant out from over there. Now, maybe looking, you're like, oh, doesn't that look Pythagorean-ish? Because we have things squared and either being added or subtracted, yes, we should look at a Pythagorean identity. Remember, sine squared plus cosine squared is 1. If we want to rewrite it so that we have cotangents and things, then we need to divide everything by sine. That gives us 1 plus cotangent squared equals cosecant squared. So how can we rewrite this? We could subtract the cotangent over. 1 equals cosecant squared minus cotangent squared. That is the same expression that we have over there. So we can substitute a 1. So this is really cotangent times secant times 1, which we know times 1 keeps it the same. So now we're just down to this stuff. Cotangent is, of course, cosine over sine. Secant, of course, is 1 over cosine. We know those cosines cancel out. We're left with 1 over sine, and the reciprocal of sine is cosecant. This goes all the way down to be cosecant theta, simplify it down, and look, that is what we're left with. We have now proven, we've verified that identity. Great. Now here we have fractions on both sides. Which side is more simple? Neither. I think they're both crazy. But we want them to look the same. So if we don't really have a clear cut, no, this is something really nice and tangible that I can work towards, we can simplify both sides. I would only do this if you feel like it's absolutely necessary. But we're going to simplify both sides. That's what we're going to do. So I'm going to kind of draw a line straight down and keep everything with the tangents and the secants over here and the cosine over there, just to keep. And then hopefully by the end we have the same thing on both sides. So start over here on the left. Notice we have tangent squared 1 plus secant. Tangents and secants, those are related in our Pythagorean identity. And so I'm going to multiply the top and the bottom by 1 minus secant squared, again to produce that difference of squares. So that gives me tangent squared of x times 1 minus secant of x over 1 minus secant squared x multiplied by 1 minus secant squared on top and the bottom, okay? Now 1 minus secant squared of x, All right, let's consult our Pythagorean identity because that sure does look like it is going to be able to be represented. Sine squared plus cosine is 1. If we want to get tangent, we need to do sine divided by cosine. So this gives me tangent squared plus 1 equals secant squared. Okay? So notice if I try to get 1 minus secant squared x, if I want to move that secant squared x over here, I can do that. But now I have 0 over here on this other side. So that's what I'm trying to get by itself. That's that 1 minus secant squared x, which is so clearly right over there. So I need to move tangent squared over to this side. 1 minus secant squared x equals a negative tangent squared x. Oop. Notice that. So I'm going to put in a negative tangent squared x on the bottom. Yeah. Okay. The tangents cancel out. I've got a negative sitting on the outside, so it's a negative 1 minus secant x. So this is a negative 1 plus secant x, which of course, commutative property, that's secant x minus 1. That is something pretty tangible we might be able to get this other side to look like. That's our goal. We're going to try to get this other side to look like secant of x minus 1. So I only have one term in the denominator. I can go ahead and break that up. That is 1 over cosine of x minus cosine of x over itself. Of course, cosine divided by cosine is 1. Over here, 1 over cosine of x. Well, that is secant. So I do have secant of x minus 1. That worked out really well. Look at that. So it's 3 more trig identities to verify there that we just saw. These are getting, a little bit more in depth. So take a look at those.